So in this section, we're going to go through potential difference and charge distributions. So we are now entering the main content. We introduced the electric potential. We now have the equations we know to use. We want to revisit superposition, and we then want to take a look at continuous charge distributions, because that's where things get a little bit more complicated. So sometimes there are easier ways to find your potential difference, and that is going to be from the principle of superposition. So we know that the electric field of a charge distribution is just the sum of the fields of individual charges making up that distribution. What we can do is extend this to work per unit of charge. If we want to find the potential difference between infinity and point P, we can find the potential at point P by using a sum. So even though I can calculate the potential at a specific point charge, if I have a charge distribution, then there's many, many point charges that make up that charge distribution. So in that case, I have to sum it all up. And that's where things do get a little bit complicated. So we're going to go through a sample calculation with discrete charges. Okay, so now we're trying to figure out delta V with discrete charges. So here we have an electric dipole that consists of point charges plus and minus q at distance 2a apart. We're trying to find the potential at an arbitrary point P and approximate the value of potential when P is infinitely far away. So we first have to draw a diagram, and so the first thing we draw is a positive charge and a negative charge. So over here we have this being plus q, and then we have this being minus q. Between the two of them, we know that they're a distance 2a apart, so why don't we just draw that out? Where this is a, and this is a, for a total of 2a. We're trying to find the potential at an arbitrary point P. So that arbitrary point P can just be all the way up here. And we're going to assume that it's infinitely far away. That means we do have different distances to consider. We can consider this distance, which we're going to call R2, R2, I guess. And we're going to consider this distance, which is R1. And we're going to consider the bisector, or the middle part here. And we're going to call this R. So just a few things to consider. What else can we say? Because P is infinitely far away, this means that R must be much greater than A. And because we can make that assumption, both the triangles should be identical. So I'm just saying the one created here and also the one created here, the two of them should be fairly identical if P is infinitely far away. So then what kind of triangle can we make from this? The other thing to consider would be this. Oops. You can assume a right angle here and a right angle here. Doesn't matter where you look. We're going to say that this angle is theta. This is theta, so this is approximately theta as well. And what we can say is from here, we can consider this 2a cos theta based off of this black triangle with the red side over here. Right now, what we're trying to do is find individual potentials and then find the sum of the potentials because of superposition. So how do we approach this? We have to look at plus q and minus q. So for plus q, you have v plus is equal to kq over, we have r2 over there. And then for minus q, you have v minus equals 2 minus kq over r1. But by superposition, you have v total equals to v plus v minus, and you end up with kq over r2 minus kq over r1. And that is going to give us v equals 2 kq. You can cross multiply and get common denominators, r1 minus r2 over r1 r2. So that would be v, that would be the individual potentials and sum of potentials. And the next thing is to find the potential when r approaches infinity, or when r is much greater than a. So let's go down here. And we'll just say when r is much greater than a, then r is going to approach infinity. And when r approaches infinity, we can assume a few things. We can assume r1, r2, and r are about the same. We can assume that r1 times r2 is approximately equal to r squared. And we can assume that r1 minus r2 needs a bit more thinking, or a bit more thought. So what this means is r1 minus r2, you end up with this triangle over here. Just trying to... We have theta over here, and then you have 2a, and essentially you have r2 minus r1 based on my diagram, because I think this was r2. And so cosine of theta is equal to r2 minus r1 over 2a. Just keep in mind, I'm just trying to derive what we have before already. So if you already have this, all I'm doing is taking a look at this triangle, red, black, and the dotted black line. We know that this is 2a, we know this is theta, so we know this length over here is 2a cos theta. So if we use that, we should be able to figure out some sort of relationship between r2 and r1. So this is r2 minus r1 is equal to 2a cos theta, which means r1 minus r2 is equal to minus 2a cos theta. Okay, so What we want to do now is put everything we know together and try to solve for V. So we know that V is equal to KQ R1 minus R2 divided by R1 R2. We know R1 R2 is essentially equal to R squared. R1 minus R2 is minus 2a cos theta. So we have minus KQ 2a cos theta divided by R squared. And so V is equal to, if this is something that was already given in the notes, not something you have to memorize off the top of your head, but you have the dipole moment being equal to 2aq. So we can replace that and end up with minus P. So 2aq pk cos theta divided by R squared. And that would be the equation for the potential at point P coming from an electric dipole. So we just went through an example of calculating delta V with discrete charges. What happens if you have a continuous charge distribution? In that case, it really just is simpler to integrate. If you have the knowledge of integration, just do a simple one and you can get your answer pretty much right away. And so if you want to figure out the potential, you can integrate dV, and then that's equal to k dq over r. So once again, similar to calculating an electric field, we do have to calculate dq first, and then from dq we can factor out the k, anything that dq is defined as that isn't dependent upon r, and then we integrate to solve for the potential. So we're going to try that with a few practice problems. We now want to figure out the potential difference with a charged ring. And we always start with a diagram for these, but slowly things should get a little bit easier. A total charge Q is distributed uniformly around a thin ring of radius A. We're going to find the potential on the ring's axis. So here we have this being the axis of the ring, x direction. We'll just assume that. We'll have a charged thin ring of radius A. So there's my thin ring with the radius of A. And we're trying to find the potential on the ring's axis. So there's going to be a point P over here where we want to be able to figure out what the potential is. Okay. This section over here is going to hold a charge of dq, so this should look fairly familiar to everybody because that's exactly how we set things up for trying to figure out the electric field, dE. We know that this distance is r, and it's equal to, if we assume this to be x, so it'd be x squared plus a squared. So how do we solve this? We know we have to integrate. We also know V is equal to the integral of k dq over r. And we know that k is a constant, which can be taken out. But what's unique is r is equal to x squared plus a squared, and that point P is not going to change. X is never going to change, a is never going to change, so r is also a constant. So we have equals k over r integral of dq. Now the integral of dq is simply equal to q because it tells us that there's a total charge of q. So now we have v equals to k over r, where r is equal to the square root of x squared plus a squared, and we know that the integral of dq is just capital Q. So in this case, that is our potential at point P. And that's very, very simple to calculate. So I think there's also another page over here where we're trying to find the potential using a known equation. We don't even need that space to finish this problem. We now want to apply the same technique and try to find the potential of a charged disk a certain point P away. So we're going to start off with a diagram. A charged disk of radius A carries a charge Q distributed uniformly over its surface. So now we have this being our x-axis. We're going to have a charged ring, or charged disk, sorry, not ring. Okay, so like this, it's okay. A, so we're just going to assume it's solid. We're trying to figure out the potential at point P. And what we want to consider is some sort of dq. So when we talk about a dq, it's a small piece of charge. It can either be something like this, where we have a small piece of charge, or I can make it easier, and because this is a symmetrical shape, might as well make a charged ring as dq. So this is dq. We'll just relabel this as radius of A. And so for point P is going to be a certain distance away. We know that R is going to be equal to the square root of x squared plus. So now this is a little different, even though this will be x no matter what. The radius here will be different because it's no longer a ring, it's a solid disk. So we have plus r squared, where r is going to be how far up that dq is. There is a total charge of q, so I'm going to write that down first. Okay, so the next step we want to do is to analyze symmetry and find an equation for potential. So one of the important things here is we note that this is a continuous charge distribution. And because of that, we have to use v equals to the integral of k dq over r. But depending on the ring, the distance to P changes. So we can use a general form for the distance r, which we did already in green over here. And so we know that each ring contributes. So we have dv is equal to, and so just keep in mind, we have integral of dv, and dv is k dq over r, but we need to figure out dq. So dv is then equal to k dq over the square root of x squared plus r squared, where r equals to the radius of the dq ring. And so at this point, it would be a good idea to rename dv as dv ring, because this will tell me the potential from one whole ring versus the potential from one tiny sliver of surface area. So for this, we know that v is going to be equal to the integral from 0 to a of k dq over the square root of x squared plus r squared. But we can't integrate dq from 0 to a. So we must find a relationship between dq and r so that we can integrate this properly. So how do we do that? I'm just going to go to the next slide so we have more room. Okay, just going to see how much room we have here. Okay, I think that's it. We know that Q is distributed amongst all the DQs. So what we're given, Q is distributed amongst all the DQs. We know that A is distributed, that's the surface area, amongst all the dAs. Where the surface area is going to be equal to pi r squared, or pi a squared. And each tiny surface area of one ring is essentially, so if I have one of these small dq rings, I know that the thickness is going to be dr, and I know that the circumference is going to be 2 pi r, especially if this is r. So that means I have my dA, my dA is equal to 2 pi r dr, and that's going to be a small surface area. So we're going to equate both of these relationships to try and find some sort of relationship between them. I know dq over q is going to be equal to dA over A, and so dq is going to be equal to q dA over A, which is equal to, let's see, 2qr dr, the pi's cancel out, and you have A squared. So that's the relationship for dq that you can have. And keep in mind, this is a shortcut because we can use algebra to solve for this. Once you have dq, you are able to put it back into this equation for v that we have from before and solve. So we have the integral from 0 to a of 2qr k dr divided by a squared, square root of x squared plus r squared. We know that v is equal to, let's factor out all of the constants, 2qk a squared. So you end up with 2qk over a squared times the integral from 0 to a of r dr over the square root of x squared plus r squared. You can do a substitution here. What substitution can you do? You can set u is equal to r squared, which gives you du equals to 2r dr. And if we say u is equal to x squared plus r squared, then du is equal to 2r dr. Okay. So why don't we put that in here? We have 2qk over a squared. We have r equals 0 and r equals a. Du over the square root of u. We have then kq over a squared times the integral r equals 0, r equals a, u to the power of 1 over 2 du. This will then give me v equals 2. I'm just going to start solving now. We still have 2kq over a squared. And now we have the square root of u from r equals 0 to r equals a. We have 2kq. We do a change of variables back to the original one to get x squared plus r squared from r equals 0 to r equals a. And you end up with v equals to 2kq over a squared times the square root of x squared plus a squared minus the square root of x as your final answer. So finding the potential with a charged disk, it can come in different ways. I tried to use a shortcut to save some time. You don't have to use the shortcut, and you can use first principles as well. Okay, so now we're taking a look at the movement of particles. A particle with mass m equals to 5 times 10 to the negative 9 kilograms and charge 2.0 nanocoulombs starts from rest and moves in a straight line from point A to point B. Using the diagram below, calculate the speed v at point B. So now we want to figure out the speed that the particle is moving at point B. The diagram is already drawn for us. But there are a few more things that we can add to this to make our life a little bit easier. It is starting from rest. So that means over here, we know that VA is equal to 0 meters per second. At VB, that's what we're trying to find. The particle here, put this in green. We know that the particle is Q naught equals to 2.0 nanocoulombs. And we know that the mass is going to be equal to 5.0 times 10 to the negative 9 kilograms. So that's all we have at the moment. If we're trying to figure out the speed, then that means that we're going to require some kinematics equations. I have the diagram here again as well. We're going to analyze the potential and the kinetic energies. So taking a look at the particle in the middle, only electric force acts on the particle, and we know that the electric force is conservative. So that means you do have the law of conservation of energy. So you have potential at A plus the kinetic energy at A is equal to the potential at B plus the kinetic energy at B. Next, how do we solve for potential? We know it's going to be Q naught VA plus KA, which is equal to Q naught VB plus KB. But because the particle does start at rest, we can just say that there is no kinetic energy to begin with. So that means we have Q naught VA equals to Q naught VB plus KB. Okay, so what else do we know? We know that KB is kinetic energy, so it's going to be 1/2 mVB squared. So we have Q naught VA equals to Q naught VB plus 1/2 mVB squared. And all we have to do now is just rearrange for VB. Rearranging for VB, we have VB squared equals to, we're going to end up with 2 times Q naught VA minus Q naught VB divided by m. So VB is going to be equal to the square root of 2q0 over m VA minus VB. We already know some of these values. We're going to have to figure out VA and VB separately. So that would be the next step. Just going to see how much room we have. Okay, so we're going to have to solve for VA first. Let's go here. Must find VA and VB first. So VA is going to be equal to KQ1 over R1 plus KQ2 over R2. What this means is at point A, we do have to consider the effect of potential from both of the charges. There's this for A being R1, and then this being R2. And then this is simply Q1 and Q2. So we do have to consider both. And so that's going to give me 9 times 10 to the power of 9 Newton meter squared per Coulomb squared. And this is 3 times 10 to the negative 19, negative 9 coulombs divided by R1, which is 1 centimeter, which is 0.01 meters squared. Let's put back. And then this is that should be equal to plus 9 times 10 to the 9 Newton meters squared per Coulomb squared. Q2 is negative 3 times 10 to the negative 9 coulombs divided by 0.01 meters. So with that, we can put that into a calculator and we get 1350 volts. Now, if you do the same thing with VB, you should get minus 1350 volts. Now, between the two of these, we can now solve for little VB, the speed. VB is equal to the square root of 2q0 over m VB, or VA minus VB. That's going to be V. Q0 is 2 times 10 to the negative 9 coulombs. We have VA being 1350 plus 1350 volts divided by 5 times 10 to the negative 9 kilograms, and we get the speed to be 46.4758 meters per second, or we can round it up to 48 meters per second. And that would be your answer to solve for VB.